Hey guys, Quiff, the Lazy Geek here, and welcome to part 3 of starting astrophotography for lazy people. And today we're not going to talk too much about the equipment. We're actually not going to talk about how to choose your telescope or how to choose your camera, how to choose your mount, or how to choose any of these things. We're going to talk about some principles that we need to understand before we start going further. In the next episode I want to talk at least about choosing the telescope, and I'll probably do it together with choosing the camera, and it will become clear very, very soon. Now, when you take astrophotographs and you show them to other people who are not photographers, one of the first questions they might ask is like, wow, what zoom level is this? What magnification is this? And then you can just like smile a bit like, and you kind of whisper like, it's not hard, this works. Because we'll get to this, but the real question would be, what was your focal length? What is your sensor size? Or more appropriately, what is your field of view? And what is your resolution? And so we're going to get there. But first things first. Okay, we're trying to image some objects that are very, very far away. And very often, I mean, now we kind of do, but many of those objects, we don't know how large they are precisely. You know, in terms of absolute terms, how many kilometers, how many, well, most of the time light years do do those objects actually cover? Well, and it comes back to a problem. How do you measure objects that are far away, and you don't even know how far away they are, so you don't have any reference point to actually give a precise measurement of the object. So one of the solutions could be something simple. Let's say I want to measure that camera there that is taking this current movie or video. So I could, take a ruler at arm's length and say like, okay, this camera measures roughly 5 centimeters when I hold the ruler at arm's length, which, it will work for me most of the time. If I keep my arm very fixed, very still, and I do it for other objects, I would be able to compare the relative size from my point of view of different objects. So I can measure, back there's a building, and I'm going to assume that my arms have roughly the same length, and that building is 4.5 centimeters wide. That kind of stuff. Very simple type of practice. But I could say like, okay, we measured 5 centimeters, but then if I fold a bit my arm and now I look at how much the camera is covering, I can see it's covering roughly 2.5 centimeters. So I really need to make sure that my ruler is always at the same distance from my eye, and it's a measure, and since my arm is typically of a different length than other people's arms, then it's a measure that I cannot really share and compare with other people's measurements. So that doesn't really work. But what we can do is and I'm going to exaggerate that angle, we can measure, like draw a line from the left-hand side of the camera, let's say. Okay, we're drawing a line, and we can draw a line from the right-hand side of the camera, and we're drawing a line. And what we can take is, instead of any distance, we're going to take those two lines that go from the center of me to the left-hand side of my camera, and from the center of me, so the same point, to the right-hand side of the camera, and we're just going to measure the angle between those two lines. And then I can actually measure like relative sizes very easily without needing a measurement method like my ruler method that works only for me because only me has this precise arm's length. I can use something that is absolute, and I can compare all across everything. And that's the concept of angular sizes of objects. So for example, the moon, if you look at the moon is actually roughly half a degree of angular size. It varies because it gets closer to the Earth, and sometimes you hear about supermoons where the angular size of the moon is slightly bigger than when it's the furthest away from the Earth, that kind of stuff. So the moon is only half a degree. Some objects that we look at are much wider than that in terms of pure arc angle. So the arc angle doesn't tell you how big in absolute terms the object is. It tells you how big from your point of view, looking at that object, how wide it is on the horizon for you. So that's field of view. And okay, how do you compute that field of view how do you compute the field of view of a telescope and a camera, or a lens and a camera together? Like, how much of the object can I cover with this combination? Well, we go into something more, which is, first we're going to talk about the focal length of the telescope or of the lens. Like most of the, if you look at a camera lens, even cheaper cameras usually have this number, or a telescope, or anything like that, you'll see something written on the lens, and it will be a focal length. And the focal length, taken together with the size of the sensor in your camera, will be able to tell you the field of view that this camera can capture. If the field of view that the camera can capture is larger than the angular size of the object that you're trying to capture, you'll be able to capture that whole object in one go without having to do things like mosaics, where you take multiple frames and then you stitch them together later on. So that gives you a good idea. So basically I'm probably showing on the screen right now a picture of my camera, the camera I'm actually using right now to take this video, and you can see there are numbers at the bottom of the lens. And on the right hand side of those numbers, so you have 10.9 to 34 that is written. That is the range of focal length that my camera can support. And if you actually, so 34 is the largest focal length it can support, the focal length where the camera actually zooms the most, and 10.9 is the lowest that the camera can support, where it zooms the least. Or in other words, the largest is where it has the narrowest field of view, and the smaller is where it has the widest field of view. So if you take one number and divide it by the other, so 34 divided by 10.9, it's roughly 3. So you can say that my camera has a zoom of 3 relative to its widest field of view. And that's what it means when you look at a camera or a video camera or anything that says it has a zoom number. It's just the highest focal length that it supports divided by the lowest focal length that it supports. It's the ratio between the narrowest field of view and the widest field of view. It's nothing more complicated than that, but it is relative to something else. So you cannot, like when you're taking a picture, whether it's of a terrestrial object or of the stars, it's very difficult to answer the question, what magnification is that? Because magnification is relative. Okay, I was interrupted. We just had our daily loudspeaker announcement that we are in an emergency kind of measure in this prefecture still. Yeah for coronavirus. Okay, so we were talking about field of views relative to our arc angle measurements or angular sizes of objects. And there is a very easy way, and I'll show that later, of how to compute the field of view depending on the focal length of a telescope or for camera lens and the size of the sensor. And spoiler alert, well, if the sensor is very small, you'll have a narrower field of view, which kind of appears like you zoomed in actually. Whereas if you have a very large sensor, then you'll have a wider field of view. With the same telescope, if you compare the narrower sensor with the smaller sensor with the larger sensor, it will look like the smaller sensor will have zoomed in more. If both sensors have the same number of pixels, then you could say that you could kind of think that the smaller sensor is superior because it gives you the same amount of pixels for a field of view that's narrower, so I get more details on my objects, which is true, but also not true. And I'll get that to in a moment. But this, what I just said, alluded to something else that needs to be considered, which is, okay, we know the field of view that is covered by my camera sensor for this particular telescope. What is the field of view that is covered by a single pixel on my camera sensor with this telescope? That's another important question, because each pixel basically represents the lowest amount of details, the smallest detail that I can actually capture. It actually represents less than that, but I'm not going to get into that right now. So each pixel, you want to know the field of view of each pixel to know the angular size of the detail on the object that you're imaging that is the smallest that you can actually capture. And this is called the resolution. Okay, so we have the field of view is determined by the sensor and the telescope. The resolution is determined by the pixel and the telescope. So the smaller the pixels, the more resolution you'll have. Yes, and I can give you an example where if I had an improperly matched field of view and resolution to my object, you can probably see right now my standard sunflower galaxy picture, and this is the same sunflower galaxy picture if I had a much lower focal length and I had only 50 pixels roughly to cover that whole galaxy, 50 pixels of width to cover that whole galaxy. The result is slightly different, right? We have less detail per pixel because each pixel was covering a larger field of view, so the resolution was worse with those larger pixels relative to the object that you are targeting. There are problems with smaller pixels. A smaller pixel will, in absolute terms, collect less light from a target for an equal focal length. And let me explain that. A smaller pixel covers a narrower area of that target. That means it captures smaller details, but at the same time, the total amount of light that comes from that particular smaller detail is also fewer photons. So that means there are fewer photons reaching that smaller pixel. A bigger pixel will capture less details, but because it covers a wider area of that object, it actually receives in total more photons in a given length of time. So you're sacrificing resolution to get more photons into your pixel, and that means that you can make your pixel convert those photons into electrons faster. Now there's a whole video I have about how this, not how this works, but what all of the parameters of a camera are, and I'm linking to it above right now if you want to have a watch, but it's more advanced topics. But let's say that there are significant disadvantages to having smaller pixels compared to larger pixels with a larger focal length. Okay, so there's tons of parameters to consider there. So now we've looked at the field of view, we've also understood what magnification is for a standard camera, and we've looked at the resolution. And field of view and resolution are the two main parameters that you want to look at. And let's go inside to go into a bit more detail. So we have a tool where we can compare the angular size of a target with a field of view of a telescopic system. So see you in a few seconds inside. And poof, I am inside. And we're now going to have a look at a website called astronomy.tools. So if you go to astronomy.tools, you'll be greeted with this homepage here, and you can click on FOV calculator, and FOV stands for field of view, which is what we've been talking about, which is determined by your focal length and by your sensor size. Now, let's have a look, and we can see there's a visual mode, there's a binocular mode, and there's an imaging mode. We're going to go into the imaging mode, and we can choose a reference object that we would like to capture. For example, the Lagoon Nebula. And we can choose a telescope, and I'm going to choose a telescope that's something that I kind of always wanted to buy, and I never bit the bullet. I wanted to buy the William Optics Star 71 telescope series, makes an equivalent telescope, and you can see it has a focal length of 347 millimeters. It has an aperture of 71 millimeters. We'll see very soon why the aperture is important. And we're going to choose a camera, and I'm going to choose my current color camera to see how well it would match. And my current color camera is the ASI 533MC Pro. Now, don't fret if your telescope is not listed in here. You can always input manually the focal length and the aperture. And we can see now that we get some results. So I'm going to add this to view. And what we can see is that we have my field of view is the red square here, and it's comparing it to basically the angular size of the Lagoon Nebula. And we can see that I would be framing with this little refracting telescope very well the Lagoon Nebula. So it gives me a very good idea very quickly. Now, if I were to try something else like the Hercules Globular Cluster, we're going to see that the main object is much smaller in my field of view. So I have a field of view that is much wider than the actual object. Is this acceptable to me? Well, I can look at something else, which is the resolution here. And I can see that I have roughly 2.23 arc seconds per pixel. Now I already mentioned arc degrees, right? One arc degree contains 60 arc minutes, and one arc minute contains 60 arc seconds, which means that in one arc degree we have 60 times 60 are 3,600 arc seconds. So you can tell how very small of an angle an arc second is. It's 1/3,600th of a degree. And the best part is that that's roughly the precision with which you want to track stars as they move across the sky. So good luck. That's what makes astrophotography so challenging, or one of the things that makes it so challenging. So we have 2.2 roughly arc seconds per pixel. Now we could look up on Wikipedia or somewhere what is the actual size, the angular size of the main M13 clusters. And I just Googled it and I found this website here that tells me that it is 16.6 arc minutes wide. Okay, so one arc minute is 60 arc seconds, right? So I can transfer that into arc seconds just by, opening up my calculator and saying 16.6 multiplied by 60, and we'll see that the diameter of the object is 996 arc seconds. So how many of my pixels will fit in 996 arc seconds? I can go back to here and I know that I have 2.23 pixels per arc second. So I can simply divide this number by 2.23. And we can see that's 446 pixels, which means that this little area, the diameter of the main part of the cluster, I assume, will be covered by 446 pixels per 446 pixels, which is, it sounds a bit low, but it's, enough for Facebook or that kind of stuff. And it also means that it's fairly easy for you to get a picture like this, where you not only take the main object, but also the star field around it, which is also a very good idea, and you can get very good pictures from that. But using this tool, it gives you a great idea of what your resolution is and what your field of view is compared to the angular sizes of all of the targets that you want to get. If I were to look at the Crab Nebula, I can see it gets really, really small. So my setup here might not be fit for imaging the Crab Nebula. I could keep the same sensor and go for a telescope with a bigger focal length, or I could get a sensor with smaller pixels. But again, there are significant drawbacks to smaller pixels. But still, if I were to use another camera with the same telescope, one camera that is well known for having very small pixels in the ASI lineup is the 183. And if I were to use the 183 instead, which has much smaller pixels, well, we'd see the same overall field of view, but you can see that my resolution now has dropped to 1.42 arc seconds per pixel. So I would get a better resolution on the actual planetary nebula itself. Again, drawbacks with smaller pixels, and also one of the things that you'll often see is something called the focal ratio. And the focal ratio of a lens or a telescope is its focal length here divided by the aperture. And if I do this on this calculator, so I do 347 divided by 71, I see that it's roughly 4.9. Look at this little number here, f4.9. Or if we look back at this camera lens here that I showed a picture of earlier, and I'm showing it again now, I see that my focal ratio is oscillating between 1.7 at the widest field of view and 2.8 at the narrowest field of view. Interesting. And so here I just basically took my focal length, divided it by the aperture. The reason for that is the bigger your aperture is, the more light you're collecting, like overall, right? If you have a 20 centimeter wide telescope, like my Newtonian telescope upstairs on the roof, then I collect much more light in total than a small camera lens. But at the same time, the more I zoom in, the better the resolution will be per pixel, but the fewer photons, because I'm looking at a smaller detail, the fewer photons will actually reach each of my pixels in a given length of time. So it gets all, it's all a compromise in the end among a lot of factors. And by dividing my focal length, which basically tells me like, okay, how much I have reduced the amount of light that goes to each pixel by making each of my pixels having a better resolution, capable of capturing more detail, and I'm comparing it to the aperture, which determines how many photons I am collecting in total. We get this focal ratio figure, which is a very, very convenient figure to see how much light comes into each of my pixels and how long I need to expose for each of my photos. And that's one of the things as well, because in astrophotography you cannot expose for hours and hours on end. You take many shorter exposures and you'll end up by stacking them. And the length of each of those exposures depends on a variety of parameters, one of them being the read noise of each pixel compared to the amount of signal that comes from the target object. And that amount of signal in a given length of time, so your exposure time, depends on the brightness of the object you're imaging, but also on your focal ratio. And the focal ratio is a very weird thing in that if I look at a focal ratio of f2.8 and I compare it to a focal ratio of f2, I will actually need twice the exposure time at f2.8 than I will at f2 to achieve the same result. So that's why this focal ratio is very much looked at a lot, and you have specialized telescopes like the RASA telescopes from Celestron that have very fast focal ratios. So the lower the focal ratio, the faster your lens is. And they have something like an f2 focal ratio, but at the same time they have a very wide aperture. And they're great telescopes as well. One of the things as well, talking about resolution, is that you get a resolution per pixel. There is such a thing, even if you didn't have the problem of how much light is collected by each pixel due to the pixel surface area and how much detail it is capturing. Even if you didn't have that, there is a point where you can have too small pixels or too many pixels. And for example, we have atmosphere, and here in Tokyo the atmosphere is usually quite unstable. There are currents of air in the higher atmosphere that are constantly moving around, and that basically blurs the details on my objects. And if my atmosphere, and this parameter is called it's called the seeing, if my seeing caused by the atmosphere turbulence limits the size of the details that I can get because they're blurry to something like 2 arc seconds, then it makes no sense for me to have a resolution of, let's say, 0.3 arc seconds per pixel. My pixels are too small. Another word for that is that I am oversampled. Now, what would be a proper sampling for 2 arc seconds of the smallest size of details that I can capture because of the atmosphere? Well, it would actually not be 2 arc seconds per pixel, but it would be something like 1 arc second per pixel, maybe even slightly less. This comes to a sampling theorem that I'm not even going to get into. But roughly, if the smallest detail that you can physically capture, either because of the seeing and the atmosphere or limitations of your telescope, the bigger the telescope, the more details it can actually drill down into. So if I take that number, the smallest amount of detail that I can actually capture physically, I divide it by 2, that's roughly the sampling that I may want to get for my pixel size. And if I'm oversampled, my pixels are too small compared to the focal length, and they have too high of a resolution that's kind of wasted. I could afford to get bigger pixels instead and get more light per pixel. On the other hand, if I'm undersampled, then my pixels might be too big compared to the amount of detail that I'm trying to capture. But then Too big is more of, you know, it's an eye of the beholder kind of thing, because do you actually need to be at the limit of the detail that you can actually capture? There are many instances where you don't need to be like that. The M13 example that I gave a moment ago is one such example. I may not need to have like all of the super small details in the globular cluster. As long as I have a very nice picture with the cluster and the surrounding star field, I'll be fine, kind of thing. And there are things you can do to kind of counter or compensate for undersampling as well. One of those techniques is called dithering followed by drizzling. And I'm not going to go into details right now, but I will say that from my point of view, it is better to be undersampled than it is to be oversampled. And again, it is something that we should not think too much about when imaging, but when choosing your telescope and a matching camera, it will start to matter. So, okay, this was a long video with a lot of principles that I touched upon. It's going to be useful for choosing our telescope and our camera to work with. And you know, everything is critical in the end to get a very automated and very easy to process, very, you know, nice to operate setup and workflow. So thank you so much for spending the time to understanding all of those principles with me. I hope that this video was useful. If it was useful, please click like, and also very important, don't forget to subscribe and maybe click the notification icon as well to make sure you don't miss the next episode in this series. And the most important, don't forget whenever you can to look up at the stars. And I'll see you next time.